Now, these machine learning models need accurate evaluation to ensure they generalize well to unseen data. So today we will understand this cross-validation, which is a technique that accurately evaluates model by dividing data into multiple folds and training them iteratively. So let's start with what is cross-validation. So basically this cross-validation is a technique used to evaluate the performance of model and ensure that it generalizes well to new unseen data. And it is a crucial step in the machine learning process as it helps to prevent overfitting, which occurs when a model is too complex and memorizes the training data instead of learning the underlying pattern. So imagine you are a detective solving a criminal case. So you have a set of evidence such as fingerprints, DNA samples, and a witness statement. And your goal is to create a model that can help you identify the perpetrator based on the evidence. So in traditional model evaluation, you would split your evidence into two sets, that is a training set and a test set. And you would use the training set to build your model, and then you would use a test set to evaluate the performance. However, this approach has a problem. That is, the test set might not be a representative of the real world case you will encounter. For example, if the test set only includes evidence from a specific neighborhood, so your model might perform well on this particular set but fail when presented with the evidence from a different neighborhood. So this cross-validation addresses this issue by dividing the data into multiple subsets of folds using each subset as a test set in turn and returning the model on the remaining data. So this way you will get a more accurate estimate of the model's performance on unseen data, and you can ensure that the model has learned the underlying pattern and is not just memorizing the training data. So simple example of cross-validation is k-fold cross-validation. So imagine you have 10 pieces of evidence and you would split your data into 10 equal parts. That is the folds. You would use 9 of these parts to train the model and remaining part as the test set. You would repeat this process 10 times using a different fold as a test set each time. So at the end you would average the performance of the 10 iterations to obtain a model's robust estimate of the model's performance. So to summarize this, we can say cross-validation is a technique used to evaluate the performance of a model and ensure that it generalizes well to new unseen data. So by dividing the data into multiple subsets and using each subset as the test set in turn, cross-validation provides a more accurate estimate of the model's performance and helps prevent overfitting. Now the types of cross-validation. So first I will understand what is k-fold cross-validation in details. So basically this type of cross-validation is the most commonly used one. So in k-fold cross-validation, your data is split into k equally sized parts of the folds. So the model is trained on k-1 of these parts and tested on the remaining part. And this process is repeated 10 times with each fold being used as the test set once. And at the end, the performance of the k iteration is averaged to obtain a more robust estimate of the model's performance. So imagine you have a box with 10 apples and you want to evaluate your model's performance. So you would split the apples into 5 groups or the folds of 2 apples each. You would train your model on 4 of the groups, that is 80% of the data, and test it on the remaining group, that is 20% of the data. And this process would be repeated 5 times with each group being used as the test set once. Then next comes leave one out cross validation. Well, this type of cross validation is computationally expensive but provides the most accurate estimate of the model's performance. So in this leave one out cross validation, for each iteration, the model is trained on all data points except one, and the performance is evaluated on this left out data point. And this process is repeated for each data point in the data set. So continuing with this apple example, so if you were to use leave one out cross validation, you would train the model 10 times with each iteration leaving out one apple as the test set. Next comes this holdout validation. Well, this holdout validation is a straightforward approach that involves splitting the data set into two sets, training set and a test set. Now this training set is used to train the model and the test set is used to evaluate the performance of the model. So typically 60 to 80% of the data is used for training and remaining 20 to 40% is used for testing. So using our apple example, we would split the 10 apples into two sets. That is, a training of 8 apples and test set of 2 apples, and the model would be trained on 8 apples and tested on the 2 apples. Then comes the stratified cross validation. Well, this type of cross validation is useful when the data set is imbalanced. Imbalanced means one class has significantly more instances than other. So this stratified cross validation ensures that each fold has a balanced representation of classes. So imagine you have 10 apples in your box, but 8 of them are red and 2 of them are green. So in k-fold cross validation, the folds might end up with an imbalanced ratio of red to green apples. But the stratified cross validation would ensure that each fold has balanced representation of red and green apples. So to summarize this, we can say cross validation techniques are used to evaluate the model performance and ensure that it generalizes well to a new unseen data. K-fold cross validation is commonly used and balanced approach, while leave out cross validation provides the most accurate estimate but at the cost of increased computation. Holdout validation is simple approach that splits the data into training and testing set, and this stratified cross validation is useful when you are dealing with imbalanced data set. So to understand this better, let's discuss the Python code for cross validation. So this Python code is a step-by-step example of how to perform k-fold cross validation on a machine learning using the popular scikit library. So first we will import the necessary library. That is, you will import the necessary libraries like NumPy for mathematical operation, load arrays from the sklearn.dataset to load the arrays dataset, logistic regression and linear discriminant analysis for building classification models, k-fold for performing k-fold cross validation, accuracy score for evaluating model performance, and cross-val score for performing k-fold cross validation. Then you will load this arrays dataset. That is, this load arrays dataset function from sklearn.dataset will load the well-known arrays dataset, which consists of 150 samples with 4 features each. That is the sepal length, sepal width, petal length, petal width. And the target variables has 3 classes: arrays setosa, arrays versicolor, and arrays virginica. And then in the next step, you will define the model to use. So in this example, we are creating an instance of linear discriminant analysis class, which is a linear classifier used for multi-class classification problem. And then you will perform k-fold cross validation. That is, the k-fold class from sklearn.model selection is used to perform k-fold cross validation. Now this n splits. This parameter sets the number of fold. So in this case, we are taking it as 5. Then shuffle true ensures that data is shuffled before splitting. Random state 42 makes the result reproducible. Then we will evaluate the model. So that is the cross-val score function from sklearn model selection is used to evaluate the model performance on each fold. And this function returns an array of accuracy score for each fold. You can print the average accuracy also. So to summarize this, we can say that this code demonstrates how to use scikit-learn to load a dataset, define the model, and perform k-fold cross validation. So this process helps evaluate the model performance and ensure that it generalizes well even to the new unseen dataset. Thank you.